Well, good morning. Thanks very much for getting up so early in the morning. What I'm going to do is approach this by first looking backwards, because one way of predicting the future is to look at history. So I'm just going to walk you through the fact that things that we used to think were hard are now trivial or easy. And that, in fact, we're moving to a new architecture in which we have to deal with the information avalanche. And all of the problems that we've dealt with in the past are going to be trivial compared to what we face coming up. And I believe that that's forcing us to a completely new structure for database systems, in which they're essentially an information ecosystem. And there are lots of different information sources that need to be interoperating together and unified. And that forces us to re-architect the way we treat information. So let's start, though, by looking at the past. That picture up on the right, those washing machine-like devices, those are disks. Each of them is 100 megabytes. Okay? 800 gigabytes in a row of disks. That's about a multi-million-dollar computer that we're staring at there. And it's the case that the most expensive thing about that computer are the people. Some of them are shown in that picture there. And the goal in that era was to be able to do 1,000 transactions a second. I've been going around saying that my little laptop, which is sitting down there somewhere, at least it was a few minutes ago, could run the financial network of the planet circa 1980. 1,000 transactions a second is a huge number of transactions. Okay? But about, I don't know, 6 or 9 months ago, I decided to try it and see. So I coded up the transaction, which is now about this long in SQL, and dropped it onto SQL 205. And lo and behold, this little critter here does 8,000 a second. And so we are well beyond. And so there's a 7-page, and it's at the end of the slides, a 7-page article on my website that has the transaction, has the thing to load the database, has the transaction profile, has the simulator that drives it, and has 3 pages that describes the benchmark. So a related thing is that it's pretty easy, if you believe that Moore's law is going to keep going, just to predict the future, at least the performance future. And I've been wondering, how have we been doing over the last N years as gigahertz has been going up and up and up and up? And an interesting graph, and you can look at it here, is the red line is an average from about 1995 till the present of how many transactions per minute, TPMC, we've been delivering. And you can see that the red line has been going up, and it's been going up approximately, the red line is the moving average. It's been going up approximately at a factor of about 30x every 10 years. It's about a 30x improvement. And the little graph in the bottom is the transactions per megahertz. And what happened is in the early days of TPCC, the graph went way up because we were learning how to make the transaction work at all. We fixed the performance bugs. And it stabilized at about 10, and then it started drifting down. And then 64-bit addressing, or an AWE, came along, massive main memory came along, and it got back up to 10. So we're tracking the megahertz pretty well. What's happening with processor megahertz these days is that we're going to multi-core machines. So you're not getting more megahertz in the standard way. You're getting more megahertz by having multiple cores. But the database guys are very good at being able to use the multi-processing that comes both with multi-socket and multi-cores per socket. So I'm expecting that we'll stay in this approximately 10 transactions per megahertz for many years to come. And we're going to be getting lots more megahertz through the multi-core approach. So the other thing, that just shows you the sort of the hardware progress. There's also been an incredible improvement in software in that time. And so the price performance of systems has actually gone up about 100x every decade. There's been a slight improvement, and so this is showing the TPC-A and then its replacement, the TPC-C, price performance, over about a 20-year span. So what does that mean? Well, it means that things get 100 times better every decade. And what does that mean? Well, that means that a billion-dollar job, which I think most of us would wince taking on a billion-dollar job, is in 10 years is going to be a $10 million job. And a $1 million job, which is probably the scale of the jobs that many of you are undertaking today, is going to be a $10,000 job in 10 years. Which is almost something that I mean, that's, I don't know, a few days, a few weeks. Okay. And today, you are routinely dealing with a terabyte to 10 terabytes. You can buy a terabyte for $500 from PriceWatch. Okay. You have to power it and package it and so on, so it'll actually cost you more like $1,000 when you actually get it configured with a processor and memory and so on. But terabytes are, we used to call them terrorbytes because we were just so terrified of them. But at this point, a terabyte is something that you just treat like an ordinary thing that you can buy on your expense account. Okay? It's less than $1,000, and therefore you can just get it without manager discretion, basically. In a decade, you're going to be facing petabytes. And I am terrified of petabytes. I have the same fear of them that I used to have of terabytes, frankly. Okay. An implication of the fact that this stuff is so cheap is that you can afford to store everything. You don't have to throw anything away. If you can remember the old days of stone tablets, most of us can't. Okay? You never updated stone tablets. Punched cards were like stone tablets. We never updated punch cards. Okay? It was an insert-only and read-only database, never an update. We went to these magnetic disks, which were very expensive, and we found ourselves having to reuse the space on the magnetic disks. The day is coming when you won't be doing updates at all. The database will be insert and read. No updates, no deletes. Okay. There are a variety of things that cause that to happen. One of the things that the database community is trying to do is to figure out how we can provide you a very convenient way of doing that. How can we make it so that you can have a database that you never delete anything from? The viewpoints in SQL Server, many other features are attempts to give you something like that. Okay. So the challenge is, we can capture everything. What the heck are we going to do with it? Okay. So the question, how much is everything? Well, it turns out that it's about 15 exabytes today. About 90% of the information that's created today is digital. It's growing fast. Digital is a minority still, but so the total amount of information is growing at about 10%. But by the end of this decade, everything will be born digital to a first approximation. And we, in fact, will be able to store everything. And that is quite a challenge for the information processing community. Where is all the data going to be? Most of the data is going to be at the edge of the network. Most of the data is going to be in cell phones, in PDAs, cameras, sensors, camcorders. Okay. So we have smart objects everywhere, and it turns out that those objects are going to have in them at least a terabyte of storage. Again, take the numbers and multiply times 100. Okay, your PDAs not atypically have a gigabyte, they're going to have 100 gigabytes of storage. They're all going to need databases. And they're all going to want to talk to each other. So we're going to need an Esperanto to allow all of these different stores to talk to one another. So what is the perfect system like? What's our goal? What are we aiming for? Okay? We're aiming for a system that stores everything. It knows what you want to know. And it tells you the answer in a way that you can easily understand before you ask the question. Okay? So, you know, our current mode is we ask, it answers. But an ideal system, we wouldn't have to ask, right? A lot of this dashboard stuff is trying to get the answers in front of you before you ask the question. That's a current attempt to do that. But one of our goals should be, let's build information systems that are constantly asking the questions for us. When the answers are interesting, it pops up. Okay? So it tells you the question you should have asked rather than the question you did ask. Or it answers the question you should have asked rather than, okay. And of course it's inexpensive and easy to manage and so on. And perhaps not everybody wants this, but there are a lot of organizations that want a system like this. One of the scary things about the fact that we can record everything is that it's easy to record things. It's hard to manage them. The most expensive part about data at this point is the cost of owning it. Not the capital cost, but the people cost. So we somehow have to bring down that cost. And much of the things that you've heard about this week are Microsoft's attempts to bring down the cost of management. But there's lots more that can be done to make it easy to manage things and to make the data essentially self-managing. Okay. So, to repeat, I think it's the responsibility and challenge of the people who are the vendors to try and make information easy to capture, easy to organize, easy to access, and easy to visualize. Okay? And there's only so far we can go because we don't understand the data we're storing. That is to say, Oracle, DB2, SQL Server, they're all storing bytes to a first approximation. Maybe they know a little bit about the bytes. The people who actually know about what's going on with the information are the people who are doing the application. So an awful lot of the intelligence about how to organize and visualize the data has to come from the people who build the applications, because they're the ones who understand the data and can add the understanding. There's a big gap between what we've got and what we want. So, first part of the talk, I said looking backwards. If history is any guide, in the next 10 years, things are going to be 100 times easier in many dimensions and 100 times cheaper. Looking forwards, we clearly have this avalanche of data heading our way, and we have some tools to manage it, but not very good ones. And the big challenge, I think, is to come up with those tools. And right now, we are at a watershed. I think SQL 205 is an example of that watershed. We are restructuring our information stores to be an ecosystem. And I'm going to talk for the next part of the talk about that restructuring. So the restructuring is that we have to reunify programs and data. We have to really get serious about encapsulating the data and at making intelligent data. When we do that, we sit down and we objectify each field. I've been working with scientific data, so I've been working with people in astronomy to try and figure out, well, just exactly what is a star and what is a galaxy? What's the object model for a star and a galaxy? I've been working with people in bioinformatics, so just exactly what is a gene and what is a protein? How do you represent them? And it turns out that there are many layers of representation for such things. But having a representation, essentially in Esperanto, that allows all the people in astronomy to be able to use the same representation or exchange the same representation for their objects is going to allow us to build a global information store. And we can't build a global bioinformatics system or a global astronomy system until we have this Esperanto for each of those languages. And you can't do that by just having data. You have to have data plus behavior. So once we have that Esperanto, we need to have a way of gluing the information stores together. And you can see this going on inside of Microsoft. You've probably heard about something called WinFS. WinFS is an attempt by Microsoft to objectify contacts and documents, okay, events. Okay. So it's fine for the Microsoft people to be off objectifying their stuff, but trust me, the Microsoft guys are not going to objectify what a gene or a protein is. It's just not what they know how to do. I think a lot of the action is in this objectification of information. Has to come from the people who understand it. Again, I think it has to come from, largely from you folks working with the domain experts, because it requires some computer science expertise and a lot of expertise from the domain. So things are really screwed up right now, is my model. And I think it all goes back to COBOL. And you laugh, okay? But there's something called Conway's Law. And Conway's Law is that systems reflect the organizations that built them. Systems reflect the organizations that built them. And the people who built COBOL had a data division and they had a procedure division. And the data guys were allowed to do data. And the procedure guys did procedures. And so the database task group had no code. It only had schema, only had DDL, essentially no DML. All the DML was hiding off in the procedure division. Okay, and this has gone on for many, many years, and when I say many, like 40. Okay. And it's as though data and code were separated at birth. Okay, well, we've been struggling. There was going to be object-oriented databases and blah, 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 but well, finally there. All the vendors now have a pretty good story about how you can add procedures to your database. And the basic idea is that you take the object-oriented methodology that you find in all the good programming languages, classes and methods, and you say, okay, what does this mean for databases? And you build what's called an object relational system. And you don't, and this is what we database guys did the first time. How do you add objects to databases? That is the wrong question. Many people asked that and answered that question, and they got the wrong answer. The question is, what kind of object is a database system? What does it do? What's the class structure for a database? Once you have that, you can now plug objects and databases together, because databases are just a kind of object, or a kind of class. So the answer, I believe, is that the fundamental thing we do is you ask a question and you get back a collection. And the collection is, in fact, a fairly uniform thing, which can be represented as a data set. You need to be able to take the answer and send it across the network, and you need to be able to send it from Oracle to DB2, and from DB2 to SQL Server, and from SQL Server to MySQL, and blah, blah, blah. Okay. All these guys need to be able to talk to each other. And it has to be general enough so that it works for MDX. And it has to be general enough so that it works for text. And it has to be general enough that it works for genomics. It has to work for NCBI, National Center for Bioinformatics. So it has to work for everybody's representation. Okay. Now, this idea was implicit in ODBC. It was implicit in OLADB, but it's explicit in the new architecture that we're coming on. Okay. So that idea, let's unify code and data, is key to this new ecosystem. There's another force that has forced all the database vendors to restructure their systems. In the beginning, life was simple. In the beginning, there were sets, there were records, there was just SQL. The original SQL spec was 35 pages long. It was a good life, okay? And then people came along and added stuff. They added text, they added cubes, they added ETL, they added time, they decided files ought to be integrated with the database, they added. And you began to have this huge collection of different data stores inside of your database system. You have to appreciate that inside of SQL Server, there's your classic row store, and there's the cube store, and there's text, and more stuff coming. Okay? So you have to be prepared for the fact that the system is just growing and having more and more stores inside the database system. It's a mess. Okay. So the solution to that mess is to go back and have a clean interface between every data source, and just treat the data stores as members of an ecosystem. And everybody can talk to everybody. And in fact, the database system emits data sets and consumes data sets. And it's just in the middle. And it provides just an environment, a space, in which these information stores can operate, and in which commands arrive and answers come back. Okay, in that world, you asked yourself the question, what's inside and what's outside the database system? And there's this classic picture of, the way people see New York City, and there's 9th Avenue, and then there's 5th Avenue, and then there's Japan. Okay. Well, there's Hollywood in between. So, the database guys, they say, well, we've got our records, and then we've got our friends on other computers, and then we have the rest of the planet. Okay? And the internet is somewhere out there in between, and there's applications out there as well. And this inside-outside model is pretty rigid, and it forces a certain kind of structure to your applications. This has been codified in a different way, originally, I think, by the Gartner Group, and says that you make a multi-tiered application, and you have your presentation services, and then you have your workflows, and then you have your business objects, and then you have your data. And there's these 4 tiers, and there's 3 interfaces between them. And so that gives you the 3-tiered interface. Well, in the world of databases, which have been fully objectified, you don't have to do that. You can say, well, the database in this new world produces and consumes data sets. It listens to port 80, which is to say it's on the internet. It's a web service. You could invoke web services, which are this objectification of data represented in XML on the internet. You send me a request as a SOAP message, and I send you back a response as a SOAP message. And so where do you put your application? Well, the answer is you can put it everywhere or anywhere. You can stick with the classic 3-tiered computing model, or you can go, and I think it's a simpler model and one I prefer, to a model in which you put everything inside the database. What does this mean? IIS goes away. Okay? You write in C# or VB or whatever language you like, and you just put your application in the database. And every processor has a database system on it, and the database system is the container for your stuff. Debugging is way simpler. I hate having all of these books. I would like to have one interface where I can write programs against, one interface that I can manage against, and I'd like to have fewer moving parts. Okay. So I think this is a direction that we're going to go, and parenthetically, on your PDA, on your cell phone, this makes very good sense. You might say in your data center that you want to have the multi-tiers for a demilitarized zone because of the attack surface problems or something else. But it is the case that in this new world, it's possible to put everything inside the database. That slide and this one, and I think the one next after it, or 2 forward, are very nicely explained in a paper by David Campbell that appeared at SIGMOD, Special Interest Group Management of Data, in June. And I noticed just a few days ago that it wasn't available on the internet, so we've just put it up on the research website. So if you go and search for it, and at the end of the slides here, there's a URL for it. It's a paper well worth reading. It describes this phenomenon. Okay, so the situation is, the first thing you add to your database is queues. Queues are just an object class. Typically, they're implemented very deeply inside the database system, but they are just a way of making asynchronous processing. Once you have queues, you have pretty much a new world. You have tight integration with your languages. You have asynchronous processing. You can put everything on the internet. If you have an idea, you can publish it on the internet. If you have data, you can publish it on the internet very, very easily. After queues, what you do is you add text and time. Very easy to add these. You just write the classes for them, and you add them to the system as table-valued functions. The other thing you do, and this is a revolution for the database community, but it fits into this model very nicely, is you add approximate reasoning. When you do text, the answers are not exact. Things match approximately. So you're forced to have in all of your answers some notion of your confidence that this is, yes, true or false. So this notion of confidence enters into all the answer sets. And when you make that a standard part of your data representation, it allows data mining operations very easily, and it, of course, allows text mining. So the key idea here is that if you can produce a table inside of your procedure and give it to SQL, you're part of the database system. So table-valued functions are the key to doing this extension. But the actual thing you're returning is, in general, a data set. So after text and time and a few other base classes that the vendors give you, the next thing that comes is data mining. And so you can see in SQL 205 and even SQL 2000 and in the other database products a lot of installments on data mining. But the real progress in data mining is likely to come from the statistical community and from people who have expertise in their particular discipline. Data mining in bioinformatics is things like BLAST and Smith-Waterman and so on. They're algorithms that are pretty unusual for us. So data mining, I think, is going to grow a lot over the next decade, largely by people being able to add their methods, their programs, into the database. The other thing is to make the database active so that when something happens, a program runs. In this new world, much of what's going on is this thing called stream processing, where instead of sending questions to the database, you send data to the database, and the database represents questions. So stream processing is a completely different approach, or sort of an inverted approach, to query processing, where the queries are in the database and the data is arriving. A third ecosystem, or an nth ecosystem, is XML, or unstructured data. Many people in the community here, I think, largely is very schema heavy. And Jennifer Whittam has advice for us. Jennifer says, everybody starts out with the same schema, which is stuff. And we just add more and more DDL until we run out of energy. Okay? So the basic story is that much of the world's information is not structured with a very strong schema. There are pros and cons of having schema. Okay? XML is with us. Live with it. Get over it. It is, for people of the next generation, it's the way most information is going to be stored and structured. So database systems are becoming an ecosystem that is many different information stores that are all going to be integrated together. The key innovations here are the unification of program and data, a standard way of representing queries and the answers to queries, and then this general mechanism for taking queries and taking many different data sources and unifying things together. One of the nice things about this is it allows you, anybody, who has information they want to publish or new algorithms for information, to put them on the internet and join this ecosystem right away. SQL 205 is a down payment on this architecture. It is the unification of program and data. It has a very impressive data mining built into it. It has very impressive semi-structured data built into it. It is an information ecosystem, and you're now in a position to add to that ecosystem.